with control circuits. So this will be topic 2 of module number 7. So power conversion. Topic 2 is control circuits. Bugger. Somebody's put in their bloody messenger notifications over the top of my screen. Don't do that. All right. Let's get straight into it. I've done a bit of work here on how to make these things a little bit better. I think I'm getting there. Hopefully the audio on this one should be much better. I've got a pretty high quality microphone recording this one. So it should sound outstanding, or it might just, you might be able to hear every noise I make every time I move. It might drive you crazy. Let's see what happens. I'm also experimenting with running this as a conference and recording it, like our video calls that we do. So I'm currently on a video call, although it is only me, and I'm recording that, and that way you'll be able to see the same screen that you're looking at now on the YouTube channel. On the YouTube channel, you'll just see the slideshow. If you're watching this on the video conference, you'll be able to see the slideshow. You'll also be able to see me, which in terms of the content doesn't make any difference. In terms of how that feels for you, it might be better to see my face. You'll see me waving my hands around. If you're on the video conference, you'll be able to see that now. If you're on the YouTube, you can't see anything. It gives us some option. So it appears that I can record these things simultaneously. So we will see how it goes. I'll record this for about 10 minutes, do this in about 10-minute chunks, and then I'll see how it turned out. So let's get into this and have a look. Control circuit. Well, let's start with what is a control circuit. So the kinds of circuits that we'll be familiar with at this time where our, if you like, control and power circuits are essentially the same thing. So what we mean there is if I have a cable, a conductor coming from a switchboard, for example, it's going through a circuit breaker, it goes through a cable to a light switch. It goes through that light switch up to my light in a room, and then the neutral returns back to the switchboard. So in that case, then the control circuit and the power circuit are the same thing. So we're just switching the power circuit by directly switching the feed going to the light, for example. With a control circuit, when we talk about a control circuit in particular, what we're talking about there is that we will have a power circuit. Obviously, we have to switch power on and off to our load, whatever that is. If we use a light, for example, we've got to switch power on and off to our light. But we won't necessarily do that directly. When I say directly, it means that the switch that I switch, the button that I push a button, push a switch, that button that I'm pushing doesn't necessarily directly control the power that goes to my light. It may control a contactor or something else, which then controls that power. A good example to think of here, I talked about it in our previous topic, is our emergency stop buttons, the start-stop buttons for our power in our practical class in 402. You'll remember that every time somebody pushes that button on one of the desks, I then have to push the button at the front of the class on the side of the switchboard. So those emergency stop buttons at the desk and then the push button at the switchboard, none of those are directly controlling the power. We're not direct switching on the power. What we have there is a control circuit that runs through all of those devices. And then that control circuit will switch on a contactor, which powers all of those, all of the outlets, all of the socket outlets in our classroom. And it's exactly the same concept as what we're talking about here. Any control circuit will use a similar or even exactly the same type of circuit as that. All right, so this slide here, control circuit diagrams. So the control circuit diagram is used to describe industrial control circuits. It shows the complete operational sequence of an installation. The diagram normally composes of two vertical parallel lines with horizontal rows of control devices between them arranged in a logical sequence. The drawing is called a horizontal orientation because the control devices are shown horizontally. Control circuits can be drawn vertically as in a vertical orientation. So if we look at this diagram here, what have we got? Well, then this would be our positive or phase side. So that line there, when we talk about our two vertical lines, we've got one here, we've got one over here. That one's going to be our phase. This one will be our neutral or negative. Give me a second. Okay. So what we're showing here is that our phase comes down, and then we have our start button. Go through our start button through our normal thermal overload, normally closed. So that means that when nothing is energized, that it's closed. It's just going to sit there. It'll be a closed switch. It'll only open when there's a thermal overload. We're going to go through our stop button, which is obviously normally closed. If I push that, it's going to open, which opens the circuit. And we go to our relay coil. That relay coil there is showing that we're switching a contact here. What does that mean? What that means is as I switch on this button here and I provide power through to my relay coil, it's going to turn on, it's going to close that contact. So when I let go of the stop button, power will still flow through this closed contact and through the relay coil. So the relay coil will hold itself on. As long as that's got power, it's going to keep this closed, and therefore I don't need to hold the stop button on. That's how a momentary stop will work. That coil will just hold that contactor on. And then how do I stop it? Well, then I have the stop button. Once I push that stop button, then the relay coil is de-energized. This contact here opens, and therefore no current flows. The stop button isn't being held down. The holding coil is open. Therefore, no power will flow. What is this circuit good for? Well, by itself, it doesn't do anything. If you're smart and you're looking at this and thinking, well, it doesn't do anything, though. It just turns itself on, which is true. But this relay coil here will also control a set of contacts somewhere else. Let's imagine that they're down here and they're powering, let's say, a motor. So then every time I push that start button, the relay coil comes in, the holding contact clicks in, it's going to close a set of contacts down here, and it's going to run the motor. If I then push the stop button, the relay coil opens, this opens, everything turns off, these contacts open, and then the motor will stop working. You will have seen this. That's, if you think about our classroom, this is exactly how it works. The only difference is we have multiple stop buttons. Stop button, stop button, stop button, stop button. Actually, all the stop buttons will be in series with each other. All the starts will be in parallel. All the stops will be in series. So if I push any of those stops, it breaks the whole circuit. Think about that. We go button to button to button to button to button. That's exactly how our control circuit in Formula 2 will be wired. Control theory, as you may know, is basic electric circuit comprises an electrical source and a load connected by two wires. The switch can be inserted into the circuit to turn it off or on. The switch then is the control device. For relatively low current, low circuit current, simple direct switching is adequate, but where the current is high and complex control circuitry is required, direct switching is unsuitable. Yeah, so that's essentially what I said before. Direct switching, our control circuit and our power circuit are the same thing. It's exactly what I said before. When we have relatively low current, and when we talk about low current, 10 amps, maybe even 20 amps, we wouldn't consider that high current for direct switching. So a normal light switch, a socket outlet, anything like that, we're direct switching. Once the current gets higher than that, then the direct switching becomes a problem. Because we need very high current switches, which means we need a lot of, we're going to need a lot of, what am I talking about? Big contacts, that kind of thing, inside that, which is going to be difficult, become more difficult and expensive to build those switches. They certainly exist, don't get me wrong, but above a certain current, they become more difficult. It's easier to do that with an electromagnetic switch contactor. The contactor, the very basic level, is very easier to replace than a large direct switch. It's just a component in a switchboard that you can pull out and swap it over, and I've changed heaps of them. I can tell you that it's pretty straightforward little job. Where we then also where we want complex control circuitry. So again, if we look at the example of our classroom 402, if we were to do that direct power switching, that means that all the power for the sockets would have to run from the switchboard out to every single one of the stop buttons. All of the stop buttons would have to be big enough to switch the entire load on every single socket in the room. And then that power is going to have to run back from those buttons back to the switchboard through the circuit protection for the sockets and then out to the sockets themselves. So we're then going to have to run big power cables out to those switches. The switches are going to have to be really big. It's just really difficult, much more difficult and costly to build a circuit like that and to build a simple stop button circuit. Just use small cables, and all those buttons are doing is they're going to be switching the power for the coil on the contactor, and then it's the coil which switches on the contactor, and the contactor switches the power for all of those sockets. This is why we would use this kind of method. Contactors relay. So heavy wiring and large control switches would be required to carry the high currents. Relays or contactors are used to solve this problem since they only require small currents to operate the solenoid coils, which form part of their electromagnets that operate heavy multipole contacts. Remember that the operating coil must be totally isolated from the contacts. A contactor is known as an electromechanical device because the switch mechanism is operated electrically. So here we have a picture of a contactor. This is what we're talking about with a contactor, and that's fairly typical. If you showed me that, I'm not going to get that confused with anything else. That's what a contactor looks like. We have here the terminals. So those are our input-output terminals here, right? So I can run my phases, 1, 2, 3 phases in the top and 1, 2, 3 phases out the bottom. When this contactor switches on, it allows power from this terminal to this one, and from this terminal to this one, and this terminal to this one. So it's just a switch across the middle. So switching the 2 left terminals, the 2 middle terminals, etc. Here, if you look really closely there, you'll see that says A1 and A2. So those are my coil terminals. So when I put power onto A1 and neutral onto A2, then this contactor is going to close, and it's going to close all the switches between those terminals here. It says here that the operating coil must be totally isolated from the contacts. That means we're not using the same power source to power our coil as we would to power our into our power contacts. Now, I would dispute that somewhat. If this was a simple push button switch where I just needed one switch, then I could just run the power off here, run that out to my switch, run back from the switch into my coil here. And that way, when I switch the power off, from the circuit breaker, then the power to my power terminal and the power to my coil will be switched off at the same time. If we have 2 entirely different power sources, there's a possibility that we could have power on here, but power off here, or power off here and power still on here, which could get dangerous, but it would depend on the situation. Without going into a huge amount of detail on all the different ways and places we might use contactors like this, it's really hard to say how we would go about doing it. So let's take that as solid advice that the operating coil remains isolated from the contacts. You can see here a sort of diagram of how this would work. Basically, this is a big chunk of metal, and this here is our electromagnet. When this part here is energized, so when I provide power into my coil, then this is energized. It just magnetizes and it pulls this part down. It just like a magnet. I have a magnet here, a piece of metal here, donk. They're going to close up together. When that happens, it pulls this down and it makes those two contacts there touch together. One of them is connected to my power coming in. One of them is connected to my output, my load. And so when they close, when those 2 points here touch together, then I have power. The switch is closed and power will run to my load. Pretty simple. Pretty simple. It's a very deep topic. All the things that you can do with contactors and the control circuits and all the weird and wonderful stuff that you can do. I really hope we get a chance before the world ends. Before the course ends, to play with some of the stuff. I do have some experiments in the back of my mind that we can have a play with here. But the actual operating principle of the contactor itself is fairly straightforward. It's a magnet and contacts that will close. Here are some pictures of some relays. So when we talk about our electromagnetic relay, it is exactly the same thing as a contactor. I can't even tell you why we use different names, relay and a contactor. All it signifies is that a contactor is a bit bigger. A relay is something small. You can hold it in the palm of your hand, and you generally use a relay as part of your control circuits. Contactor is a bit bigger, and it's going to be, I don't know, size and weight of a coffee cup, maybe. But they do exactly the same job. They work on exactly the same principle. We have contacts that open and close. We have a coil which magnetizes and closes the contacts. That's it. So if it confuses you, what's a relay and what's a contactor? Nothing. They're the same thing. Okay, now in our last topic, I talked about this. I briefly mentioned that we identify our contactors with the letter K. That means that when we're drawing them, you will draw a K next to a contactor. If you have more than one contactor, the first one will be K1, the second one will be K2. What this does is it means that we can draw a circuit so that the coil, which is a control circuit, and then the contacts, which are in the power side of the circuit, I don't physically have to draw them next to each other. I could draw a coil over on one side, and that's part of my control circuit, and I write K1 on that coil, and then I have a set of contacts over here powering the load, and I write K1 next to that, and then that coil is powering that set of contacts. And if I have more than one contactor, then I have K2, a K2 coil, K2 set of contacts. Same thing. Relays we identify by R. Again, remember, relays are just contactors. They're the same thing. Just one is smaller than the other. It doesn't actually make any sense. Now that I have to sit here and explain this, it makes zero sense to me that we would even call them different things. Okay. Look, I'm going to take a pause there. Where am I? We're about 20 minutes in. And I've gone 7 and I'm about 1/4 of the way through. Okay, that's not too bad. So I'll stop this one here. Start part 2 shortly.